Okay, so we're gonna get started today. Kind of thinking about how I want to do this lecture right now. So basically, I'm gonna write on my iPad, and I'm gonna share that screen with you, and we're gonna do the lecture that way for today. But I also made slides, and I don't think I can show them both at the same time. We'll look at that, but it doesn't matter anyways if you can't see the slides during the lecture because I'm gonna write everything down. But if you want to look at the slides while we do the lecture, you can go on Canvas, and I uploaded those. So let me share the screen. Okay, so on Canvas, I uploaded this week's lecture. So it's under week 3. And so here's the lecture, and then I also put up the lab handout as well. So again, you don't need to look at the slides during the lecture, but they might be of use, so you can check those out. I would recommend looking at the lab handout. I'm going to go over that right now, but you should make sure to download that at some point. Okay, so today we're just going to go over basically the analytic part for the first lab. So this is going to be for the submarine towing problem. So we'll go over that. We're not going to use MATLAB today. We're going to do that next time. That should take, a fair amount of time, probably like an hour or so next time. So I want to make sure that we spend like all of our energy and focus on that next time. So this time we'll just get I don't know, I guess the more boring stuff out of the way, to be honest. All right, so any questions so far for the class or what we're going to do today or next week? Okay. So first off, we're going to go over the problem description for this lab. Okay, so it's the submarine towing problem. So basically what we have is a submarine, and it's going to be towed by some towing boat. Okay, so I'm going to read the description right now. So we have a scientific deep diving submarine weighing 32,200 pounds, and it must be towed out to a sea location by a much larger ship. There's a nylon towing cable that's going to be used. It's off the back of the ship. Your senior officer has specified that 300 feet of cable will be used in the towing operation. Specifications from the cable manufacturer indicate the elastic properties of the cable are such that 300 feet will elongate 0.6 feet for each 1,000 pounds of tension in the cable. The wave and viscous drag, so basically that's going to be our dampening coefficient. That's going to be assumed to be linearly proportional to the forward velocity under tow, and from previous tests, it's equal to 1,200 pounds second per feet. And then under harsh conditions at sea, it's common to experience a jerk start, so the towing ship is going to be moving forward at a constant speed of 5 feet per second, and then the cable is going to snap tight, it's going to become taut, and then we're going to begin pulling the submarine forward, which has been at rest. So once our submarine starts moving from that kind of jerk start, that's going to define time t equals 0. All right, so any questions on this riveting problem? Okay, so we're going to get started then. So I'm going to share my screen right now. So I tested this out before, so hopefully it actually works, right? All right, so it looks not great. Who in here has like a large monitor that's like, I don't know, we'll say 24 inches or above?
I got 3.
Okay, so yeah, on your monitor, it's going to look pretty small. And I was trying to work on this before this lecture to actually have it upscale. And you can go to your view options up top, so you can basically do fit to window, but the upscaling that they have in Zoom really sucks, I'm going to be honest. So it's going to look, not fantastic. You can still read everything, so if I write something right now, oops, wasn't really going right. Okay, so if you're on a large monitor, it's going to look kind of pixelated, I guess, but so it's okay for now, but I'm trying to work on this so it's actually going to look better if you have a larger monitor. Okay, so I'm going to pull up the problem description again on my computer. All right, looks like I need to pull it up on this computer. Sorry, give me a second here. Okay, now I got it. Sorry, I have to do kind of weird stuff. If I change my screen on my one computer where I'm kind of sharing my screen through my iPad, then I can't look at anything. So I have to pull all my stuff up on the other computer. All right. Actually, let me minimize something. Okay. All right, so hopefully you guys have the handout pulled up because I can't share that at the same time right now. I was hoping I could, but I can't. So pull that up, but either way, I'm gonna, go over it, so it should be okay. All right, just making sure that I was recording. So we're gonna get started now. Okay, so I already went over the problem that we have to solve. So the first thing we have to do is do a free body diagram. So I guess actually I'll first go over the things we want to actually solve for this problem. So I'm going to share my other screen again really quick. Okay, share. All right. Okay, so here's what we have to do. We have to draw the free body diagram of the submarine. Then we're going to obtain a differential equation model for the submarine. So basically just our equation of motion. And then what we have to answer for the lab report is what is the maximum force in our towing cable and what time does it occur? What's the elongation of the towing cable at steady state? So make sure you're looking at steady state there. And then what is the maximum velocity of the submarine? When does it occur? And then we're going to have a kind of a whole new setup where we're basically just going to change the length of a cable that we have to correspond to a damping ratio of 0.707. And then we're going to kind of resolve some stuff for this new cable length. And we're going to look at the maximum velocity and the maximum cable force again. And we'll compare that to the first cable that we were using. And then the last part is you need to solve our equation of motion by hand. So you need to solve that analytically, and then you're going to compare those solutions, so the position, velocity, and acceleration, to what Simulink solved. And they should be, very, very, very close to one another. Okay, so any questions on what we have to solve? Okay, so I'm going to share my iPad again. right, so I'm going to try to make this, somewhat fast. That's what I typically like to do. I don't want to, rush through anything, but I want to make sure that we're not stuck in here the whole time. All right, so the first thing, again, we need to do our free body diagram. So let's work on that right now. So we're going to have a submarine that's being towed. So I'm going to draw this out. Again, I would pull up the slides if you can. It would help you out. Okay, so here are our submarine. It's going to be our mass 1. And then it's going to be towed by a towing boat. Okay, so we're going to call the towing boat mass 2. And then in between, K1, that's going to be the towing cable that we have. And then we're going to have some viscous drag from the waves. Okay, and then from this towing boat, we're going to say that that's applying a force T from its thrust, basically. And then we have damping that's being applied to the towing boat itself from the waves. And then for our coordinates, we're going to say that the positive x direction is to the right. So we have x1 and then we have x2. Now for this problem, we only want to look at the submarine. So we're going to isolate the submarine right now and make a free body diagram for that. Okay. I just want to make sure everyone can see my screen and read everything okay, right?
Yeah.
Yeah.
Okay, cool.
Yep.
All right, so let's work on this now. So we're going to have x2 minus x1. So hopefully you can remember what we basically did from your vibrations class. So we just we're modifying our free body diagram here. So we need to account for what we had up top here, where we had our spring right there, but we need to take into account the towing ship. Okay, and then we're going to have C x dot 1 for our for the damping. Okay, and then I'm going to draw the coordinate axis once again. So we have x1, that's going to be the positive direction. Okay, so we have our basic FBD. Now we're going to make the equation of motion that is based off of this. Okay, so we'll do EOM. So to start it off, we're basically just going to think about sum of the forces equals mass times acceleration. Or we can rewrite that as sum of the forces equals m and then x double dot. Okay, so from our free body diagram, now we're going to make that equation of motion based off of the sum of the forces. So we're going to go to, so I'm kind of going to gloss over this. So hopefully you remember what to do from vibrations, but we'll talk about it a bit too. Actually, I won't skip too many steps here. Okay. So we're going to have m x double dot equals k x2 minus x1 minus c x1 dot. So here we just have the sum of the forces equals mass times acceleration. So we have that on the left right there. And that's going to be equal to k x2 minus x1. We have that from our free body diagram up top right here. So we have positive k x2 minus x1. And then we have minus c x1 dot because that's to the left and that's going to be negative for how we defined our coordinate, the positive direction. Okay. And then I'm just going to divide everything through by m1. So we're going to have x1 double dot equals k divided by m1, x2 minus x1 minus c over m1 x dot 1. Okay, so that's simple enough so far, but if we want to solve this, we need to know what x2 is. So x2, that's the position of the towing boat, but we don't really know that, so we need to have some kind of implicit expression for x2 so we can actually solve this both by hand and in Simulink. Okay, so from basic physics, so back from like 225, you should remember, or even probably high school, our position, we can say that's equal to the velocity times the time. So that's just x equals velocity times the time, or we want to specify it for the towing boat. We'll do x2 equals v2 times t. And now we can plug that into our expression right here. I call that equation 1. And then we can simplify that. So the x1 double dot equals k divided by m1. Then we're going to plug in for x2 now. So v2 times t. And minus x1 minus c. Oops. I keep doing a mass flow rate, keep putting a dot above the m. So c divided by m1 times x dot 1. Okay, so we're gonna clean this up a little bit more. So we'll do x double dot 1 equals, so I'm just gonna multiply k divided by m1 through our expression v2 times t minus x1. So we're gonna have minus k over m1, and we have times x1 minus c over m1 x dot 1 plus k over m1 v2 times t. All right, everyone following along so far?
Yep.
Okay. All right, so now we're gonna, again, clean up the EOM. I know there's a lot of this simplification right now, but if we look at the EOM, we wanna make sure that we have everything that we need to actually solve it. So from the problem statement, we know our damping ratio, that was 1,200 feet per second divided by pounds. Did I remember the units right for that? Maybe I flipped them. I always forget them. 1,200 pound seconds divided by feet. Okay, so we have that. That was given from the problem statement. We need to solve for K. So we need to solve for our cable stiffness. We were given stuff from the problem statement to solve for that, so we can do that. And then we need to also find the mass of the submarine. And then for V2, for the velocity of our towing boat, we were also given that. If you remember from the problem statement, it said that the towing ship was moving forward at a constant speed of 5 feet per second. And then we're going to have that jerk start to start towing along the submarine. Yeah, see, Sean, I wanted to show you the slides for that reason. I'm still going to show you guys, though. Don't worry, I'm going to pull that up. All right, so yeah, basically Sean was saying, cool dog, Pat. I'm going to show you guys the slides, but anyways, yeah, you'll see that in a bit. Okay, so now we're going to solve for the cable stiffness and the mass of the submarine. Okay, so we're going to do that first. All right. So solving for the cable stiffness. Okay, so you should remember some of the forces. That's going to be equal to negative kx, where k, that's our cable stiffness, and x is the deformation of some cable. Okay, so we'll do some of the forces equals, we'll do minus kx. And then we can solve for k equals minus f over x. And then we were given the force from our problem statement. So we were told in the problem statement that we have 300 feet of length for a cable, and it's going to elongate 0.6 feet for every 1,000 pounds of tension in the cable. So right there, we have what we need to find the cable stiffness. So we have the force, 1,000 pounds, and then we have the deformation, which is 0.6 feet. So we just need to plug that in. So minus 1,000 pounds, and then divided by our deformation, 0.6 feet. And then we get our cable stiffness that equals minus 1,666.7 pound force per foot. Okay, so simple enough. Now for the mass, we need to solve for that. So we were given the weight of the submarine. That was 32,200 pounds, but we need to convert that to mass. Okay, so mass, that's going to be equal to the weight divided by gravity. So M1 equals, we'll do W1 divided by G. So again, the weight, that was 32,200 pounds. And then we're going to divide that by gravity. So 32.2 feet per second squared. And then our units right here, if you remember, maybe not, I don't know how often you use it, but it's converted to slugs directly from right there. So units for slugs is pound force divided by feet per second squared. So M1 equals 10,000 slugs. Beautiful word. Okay. There we go. All right, so to make the lecture less boring, again, I was hoping to actually show you the slides as well. I'm going to share my screen now on my other computer. So some of you already saw it. So I was planning, again, on showing you the slides here. So be going down, solve for x2. And then you would have had a surprise doggy. So there we go. Anyways, yeah, that's my dog. Her name's Kira. All right. So that didn't work out exactly like I wanted, but there you go. There's a good surprise dog for you.
I like that you added the figure title.
Yeah, you gotta know that she's a good girl. Okay. All right, so we'll go back. We'll share my iPad again. Okay. Okay, so now we have everything that we need to then start solving for some of the deliverables that we need to have for the experiment. So the first one is going to be finding the maximum force in the towing cable. Okay, so we're going to get an expression for that. So, okay, I need to pull everything back up. Kind of annoying. Zoom like messes up all of my windows. Okay, so the maximum force that's going to occur for when our acceleration is at a maximum. So if you think about that again, we're doing the sum of the forces equals mass times acceleration. So our mass is going to stay constant, or we're going to assume that it's staying constant for the submarine. And then we have the acceleration. So to have our maximum amount of force, we need the maximum amount of acceleration. Okay, so if we look back at our equation of motion, so I'm going to write this down again. Okay, so I'm going to write this one down. So it was a bit earlier on. Okay, so from this, our maximum force is going to occur for k times x2 minus x1. So I'll explain this in just a second. I'm going to write this down right now, though. Okay, so I've rewritten our equation of motion here. So I have basically force on the left. So we have mass times acceleration. Then equals k times x2 minus x1. Again, I just rewrote x2 because we know that equals v2 times t. And we have minus c over m1 times x dot 1. So from this, the maximum force is going to be the maximum value that we can have for k times x2 minus x1. Okay, or k times vt minus x. So we're not looking at the last part of our expression here, where we have the damping coefficient. We're not looking at that because we want to look at the maximum force that we can have. So you can kind of think of this like a worst case scenario kind of design thing where you want to have some factor of safety, because our damping from the waves, that's going to allow us to have less force on the cable when we have that jerk start. So in this case, we're basically assuming that our damping ratio or damping coefficient is 0. That's not really going to be the case, obviously, if we're in the sea from the viscous drag, but we're just going to assume that for this analysis here. And then you'll see next week, if we did include the damping coefficient here, that it would take our force down by about half the maximum force. Anyway, so you want to box this right here. Okay, because you're going to need that for the lab. That's one of the first deliverables that we have. And then we're going to find when it occurs. So intuitively, you should know that it's not going to occur at time t equals 0 because we need to accelerate. We're not going to have some instantaneous acceleration. It's going to be very close to time t equals 0, but it's not going to be at t equals 0. We're going to need to solve that inside of Simulink. So we're going to basically make our Simulink model, and then we'll write some code to where we can match up the maximum force. And then from that value, we can find the time for when that occurred. Okay, any questions on that? Okay. So then we'll go to the elongation of the tow cable, and we're going to be looking for this elongation at steady state. Okay, so I'm going to get our equation of motion once again here, and then we're going to rewrite some stuff. Okay, so I'm going to rewrite this where we have x double dot equals minus k over m1 x1 minus c over m1 x dot 1 plus k over m1 v2 times t. So again, remember that v2 times t, that's x2. Okay, so we want to look again at steady state. So if we're at steady state, then our acceleration is going to be 0. That's not going to be changing anymore. So x double dot, that's going to go to 0. And then I can multiply through for this equation by m1. So if I was going to multiply that out, then m1 is going to go away. So we can write it as 0 equals minus k x1 minus c x dot 1 plus k v2 times t. And then we can rewrite this where x dot 1, we're just going to make that v1. So 0 equals minus k x1 minus c v1 plus k v2 times t. Or we can rewrite that where v2 times t, that's going to be equal to x2. So I'm just going to erase that part. And we'll just put x2 right there. And then rewriting again. I like showing a lot of steps just so I can follow it a bit better once I look back on it and I'm writing my lab report personally. So that's why I have so many steps here. We can do k x2 minus x1 and then minus c times v1. Or I can drop the 1 because at steady state, the velocity of the submarine and the velocity of the towboat, they're going to be the same. Okay, so remember we need to look for the elongation for the towing cable. So we want to look for delta x. So we have delta x, that's x2 minus x1. So I'll rewrite this as k. Delta x equals c times v. So I just kind of put the c times v on the other side. And then delta x equals c times v over k. And then we can box that as well, because again, we're going to be solving for this in the lab report. All right, so this is our elongation of the towing cable at steady state. Oh, sorry, I didn't see your question. Yeah, so the derivative of displacement is velocity, so x dot 1, that's the same as v1. Yeah. All right, so we have c, that's known, that's 1,200. Our velocity, that's also going to be known, that's 5 feet per second at steady state. Or that was the velocity of the towing boat originally, but we can solve for our velocity over time inside of Simulink. And then we have k. We know what k is. We solved that earlier. That was 1,667 basically. Okay, so with this, then we can plug this into Simulink and we can find that elongation over time. Okay, so we can also solve for this a different way. So I'm going to show you, and then we're going to compare our graphs inside of Simulink next week. So let's write this as alternative elongation. I don't know. At steady state. So at steady state, they're going to be the same as you would hopefully think. But getting there, our elongation is going to look a little different before steady state using these two different techniques. So right now, this might seem a little like abstract, but once we actually solve for this inside of Simulink, it'll hopefully make more sense. So I'm going to start with the same equation that we had earlier, where we had 0 on the left-hand side. Again, at steady state, the acceleration is 0. Minus kx1 minus c times v plus k vt. So this is what we had earlier on. So I'm starting from this point, but I'm going to solve for our elongation in a different way. So I'm going to move c times v. Again, at steady state, the velocity is going to be the same. So I'm going to drop the subscripts right now. So I'm just going to do c times v equals k times vt minus kx1. And then I'll divide through by k. So we have c times v divided by k equals v times t minus x1. Well, right above where we boxed our elongation there, the elongation is equal to c times v divided by k, which is what we have on the left-hand side right here. Okay, so those are the same. So I can just plug in for delta x. Then we get delta x equals v times t minus x. So again, this elongation at steady state, it's going to be the same. But before that, during our transient phase, it's not going to be the same. And we'll look at that inside of Simulink next week, and we'll have some questions on that. But if you are in Simulink or you're writing a report, you can use either of these two equations here to solve for the elongation. Okay. So I know this is kind of dry so far. I apologize about that. But we're almost done with at least a lot of the boring stuff. Okay, so now we're going to talk about the new cable. So I guess first of all, I'm going to go back to what we have to solve for the project or for the experiment. So the first thing, if you look at your lab handout, you'll see under section C that we need to answer the maximum force in the towing cable and when it occurs. So we have our expression for that. The maximum force is going to be the maximum value that we get for K times basically our elongation. And, but of course, our velocity is changing over time. So that's going to occur at a specific point in time. That's going to be close to time t equals 0, but not quite. So we have our expression to solve for this, but basically we need to model this inside of Simulink to actually solve for it. And then after that, we have the elongation of the towing cable. So for that, we just solved for that. So we have two different methods to solve for it. It's going to be the same at steady state, but in that transient phase, it's going to be a little bit different. And we'll discuss why that's different next week once we actually make the model. And then the third question we have is the maximum velocity of the submarine and when it occurs. So again, for that, we're going to be using Simulink for that. We're going to make the model. We're going to be able to see our graph, and then we're going to write some MATLAB code to specify that maximum value and when that occurs. So a lot of what we're doing today is kind of getting the fundamental equations that we need for MATLAB next week. Okay, so now we're in part D where we need to have some new cable. So remember that we're going to have some new cable that's going to correspond to a damping ratio of 0.707. And we're doing that so we can avoid as large of a peak force in the towing cable. We want to make sure that it's not going to be as large as we have for the first towing cable. So basically our cable length is going to be longer so we can have less of an impact force. So this is part D on the lab handout. Okay, if you have Dr. Tran, he calls zeta tornado, which is pretty great. So I'm going to call this tornado. So we have zeta or tornado equals 0.707. I hate drawing zeta. Okay, so our questions here are to find the length of the new cable. And so that's basically all we're going to do right now. And then the rest of it we have to do inside of Simulink. And that'll be to find the new maximum velocity and the new maximum cable force for this cable. Okay, so let's do that now. Okay, so if you remember the damping ratio, the equation for that is going to be zeta equals c divided by 2 times the square root of km. So damping ratio tornado equals c divided by 2 times the square root of k times m. And then we want to solve for this new k2, so then we can find the new cable length. So let's rewrite this right now to solve for k2. Okay. So we have 2 times tornado equals c divided by the square root of k times m. And then 2 times the square root of k times m times tornado equals c. And I'm going to square everything here so we can get rid of the square root. 4 times k times m times tornado squared equals c squared. And then we want to find that new cable stiffness k2. So now I'm going to add the subscript 2 here. So k2 equals c squared divided by 4 times m times tornado squared. Let me rewrite that. I kind of wrote that kind of bad. Okay, so there's k2. So now we have that expression for k2. Okay, but remember we want to find the length for this new cable. So first I'm going to plug in everything that we already know so we can solve for k2 right here. So we have 1,200. Yeah, let's write out the units. I always like to write out all the units so I make sure that they can cross that, okay? So we have 1,200, and we have pound force times second squared. And then divided by feet squared. So for me, this is how I like to write everything out, where I'm carrying, the feet squared to the bottom and not keeping it on the top line. Okay, and then we have multiplied or divided by 4. And we have our mass here, which is, so Earlier I might have put, yeah, earlier I put 10,000 slugs, but it should have been 1,000 slugs for the mass. So we have 1,000 slugs, and I'm going to write the base units for that. So that's pound force times second squared divided by feet. And then we have the damping ratio 0.707 squared. And now we can cross out some of our units here. So we have second squared, they cross out. We have 1 foot there, we can cross that out right there. And then we can cross out 1 pound force. And then if you make this calculation, then you see that K2 equals 720 pounds per foot. Okay, so we want to solve for that new cable length here. So for this, we're going to use an expression that relates our first cable to the second cable. Okay, so we're going to have this linear relationship because all we're doing is increasing the length of our cable, which is also then going to change the stiffness of the cable. So we have K1 times L1 equals L2 times K2, and then we're just going to solve for L2. Okay, and then if we plug all this in, remember from the problem statement, the first cable length, that was 300 feet. And then we solved for the first cable stiffness, that was 1,667 basically. And that's pound force per foot. Putting that on the bottom, and then divided by K2. So K2 we just solved for, so 720 pound force per foot. And if we cross out our units here, we have pound force, and then foot and foot. So then L2 equals about 694.5 feet. Okay, so there we go. So let's kind of have a little bit of review here. So for the first cable, we had a length of 300 feet, and the cable stiffness was 1,700 basically. Our second cable has a length of 695 feet, and that cable stiffness is 720 pound force per foot. So that's gonna just let us have a lower maximum force on the cable, and you'll see that once we do the simulation. Were there any questions on this? Okay, so now we have everything that we need to do to solve for all of this inside of Simulink. So yeah, not the most riveting stuff. So we're going to go over one more thing here today, which is solving an ODE analytically. But before we do that, we have another surprise doggy slide. So let's show you that. Let's make this a bit better here. Okay, there's the surprise doggy when she's really little. And yes, a very young Kira indeed. This was like right around when we got her, around Christmas time. 4 years ago now. Okay.
She a golden retriever?
No, she's a yellow lab.
Oh, dude, labs are the best.
Yeah. Her leg is kind of hurt right now. She'll like limp a little. It's been like that for a few months. Okay, so now we need to solve our ODE analytically. So I'm just going to go over the ODE that I posted to Canvas. So I think a few people wanted to look at that, so I posted it. So I'm not going to go over solving the ODE for this lab by hand. I'm going to have you guys do that for the lab report. But it's going to be pretty similar to what I posted on Canvas. So I'm going to show you where that was. So we'll go to the home page, and then we'll go to week 2. Then we'll look at this link right here, analytic solution for a spring mass damper system with some external excitation. And I never typed it out, but that should be okay. Okay, so we're gonna just go over this today. Okay, so let's share the iPad once again. Okay. Okay, so just for I don't know, curiosity's sake, did you guys take 431 last semester?
Yes.
Yes.
I did.
Yeah, okay.
Vibrations, right?
Yeah. And
Yeah.
then what about 308? When did you take that?
2 semesters ago.
Okay. Well, I know when I took this class, I need a little refresher on solving ODEs, so we're just gonna go over that in case some of you do. Okay, so I'm gonna draw out our FBD here. And again, it's gonna be similar to what we have for the lab. So we're gonna have some fixed support here. Then we're gonna have a spring, we're gonna call it K. We're gonna have a damper, call it C. And then that's gonna be connected to some mass M. And then we're gonna have some external excitation. So I'm gonna write out some of our numbers right now. Okay, so you're gonna be given the weight of our block here is gonna be 10-pound force. The cable stiffness is 4 pounds per foot. And then our damping coefficient is 3 pounds times second divided by foot. And then our external excitation, that's going to be some cosine function. So we're going to do 5 times cosine of t. Okay. And just so we can get this out of the way, I'm going to convert weight to mass. So again, remember mass is just weight divided by gravity. So this will be, let's do mass equals 0.31 slugs. All right. Okay, so now we're going to write out the equation of motion here. So if we look at our FBD, we can just write this out as, again, remember we want to do the sum of the forces equals mass times acceleration. So we're going to do mx double dot equals minus cx dot minus kx plus f of t. Let's actually quickly draw a better FBD. So we have our mass here. And we have minus kx, that's going to the left. And then we have minus cx dot. That's also going to be going to the left. Then we have our force F of t going to the right. Okay, so our equation of motion, we have mx double dot equals, let me draw the positive x direction. All right, mx double dot equals minus cx dot minus kx plus f of t. And then I'm going to divide it through by m. Minus 10 points for no coordinate system. That's rough. I forget that pretty often, so. All right. So we're going to divide through by m. X double dot equals minus c over m, x dot minus k over m x plus f of t over m. Okay, and then I'm going to rewrite this now to x double dot plus c over m, x dot plus k over m, x equals f of t over m. So I just brought some terms over to the left-hand side. And then if you plug in for everything here, so we're going to plug in for c, we're going to plug in for m and k, and our function, our forcing excitation. So we're going to have x double dot plus 9.67 x dot plus 12.9 x equals 16.129 cosine of t. So not the most pretty numbers. I didn't, feel like trying to make pretty numbers here, but that doesn't matter, Okay, so at this point, what we have to do is solve for our homogeneous solution and then also our particular solution. And then we'll combine those to get our kind of, our overall general solution. Okay, so we'll start out with the homogeneous now. So with these disgusting numbers, we're going to have to do the quadratic equation. All right, so let's rewrite our equation of motion to solve for the homogeneous equation here, or solution. So remember, for that, we're just going to set our left-hand side equal to 0. Okay, and then we're going to do the quadratic equation right now. And we're going to solve for our eigenvalues here. So we have lambda 1, comma 2 equals minus 9.67 plus or minus 9.67 squared minus 4 times 1 times 12.9. I'm sure all of you are singing that song in your head right now. And then divided by 2 times 1, and we have a square root right there. Then we're going to get minus 9.67 plus or minus. So here I just, I'm doing a few steps at once. We already took the square root, so we have plus or minus 6.48. And then all over 2. And then this is going to give us eigenvalues of lambda 1, comma 2 equals minus 1.6 and minus 8.1. Okay, so we have 2 real roots here. So our homogeneous solution we can write out as x h of t equals c1 e to the minus 1.6 t plus c2 e to the minus 8.1 t. All right, so there we go. We got our homogeneous. We're going to solve for C1 and C2 a bit later on. I should have given an initial condition, so I'm going to go back up here and write that down. Okay, so our initial condition is x of 0 equals 0 at time t equals 0. Or really just our system is at rest at time t equals 0. All right, so now let's solve for the particular solution. Doing, if I remember right, it's called the method of undetermined coefficients. Hopefully you remember that. So if you remember in your book, you have like some table where, they would show you for your right-hand side of the equation what you need to use to solve for that particular solution. Okay, so for us, we have a cosine function for the particular solution. So to solve for this, we're going to write xp of t equals a times cosine of t plus b sine of t. Okay, so if you had some other, forcing function here, like, I don't know, 2x squared, then it's going to be different for how you start to solve the particular solution. Again, it's there's a table in your book, and I'm sure all over the internet, but on the top of my head, I forget what you would have to do for like 2x squared. I think you need to go down by the power, but that's been a while. Okay, so now we're going to do x dot p of t. Okay, so we're going to take the derivative here. So we're going to get minus a sine of t plus b cosine of t. And then we're going to take the derivative one more time. X double dot p of t equals minus a cosine of t minus b sine of t. Okay, so now we have all of this. Now we're going to plug this back into our ODE. Okay, I'm just going to bring the ODE down here. All right, there we go. So we have minus a cosine of t minus b sine of t plus 9.67. I guess in my notes I only did 9.6, so I'm just following my notes to make it a bit easier for me. So minus 9.6. And then a sine of t plus 9.6 b cosine of t plus 12.9 a cosine of t plus 12.9 b sine of t equals 16.129 cosine of t. All right, so lovely equation, I know. So now we're going to group our terms here. So we're going to group the sine terms and the cosine terms separately. So we'll start out with the sine terms, and what I'm going to do is underline all of them so it's just a bit more clear for us. So we have minus b sine of t, 9.6a sine of t, And then 12.9a cosine of t. Or sorry, undo sine. Yeah.
Is the 9.6 supposed to be negative?
Yeah, I just saw that too. Yeah. Okay, I'm just gonna make sure that I have all the signs right. Okay, yeah, they should all be correct now. Thank you for that. Okay, so now we have our sine terms here. So I'm gonna write all of those out. So we have minus b minus 9.6a and 12 plus 12.9b, and all multiplied by sine of t, so I just took sine of t out, equals 0. All right, so remember it's equal to 0 because on the right-hand side, we don't have a sine of t, we just have a cosine of t function. Okay, so then I can divide through by sine of t, and then we're going to get minus 9.6a plus 11.9b equals 0. Okay. Now we're going to group the cosine terms. So for that we have minus a plus 9.6b plus 12.9a equals 16.129 cosine of t. All right, and then if I divide through by cosine of t, we'll get 11.9a plus 9.6b equals 16.129. All right, so we did cosine of t, we divided through by that. That's going to go on the right-hand side, so cosine of t, that's going to go to 1. Okay, so now we have a system of equations here from our sine terms and our cosine terms, so we can solve those simultaneously, and then we can solve for the coefficients a and b. So for me, I hate doing that by hand. I'm sure you do too. So I solved that in my calculator. I'm not going to bother to do that by hand here. Or you could solve this inside of MATLAB as well. But your calculator should have some function to solve equations simultaneously. If not, use MATLAB and I can show that maybe next time if you want. Okay, so we have a equals 0.821 and then b equals 0.662. Okay, so now we can plug those coefficients into our particular solution. So remember up here we had our particular solution was xp of t equals a cosine of t plus b sine of t. Right there. So we'll plug those in right now. All right, so now we have our homogeneous and our particular solution. We're going to combine those into our general solution now, and then we're going to solve for C1 and C2. Okay, so we add for the homogeneous C1 e to the minus 1.6t plus C2 e to the minus 8.1t. And then our particular solution plus 0.821 cosine of t plus 0.662 sine of t. Okay, so now we're going to apply our initial condition. So remember, we said our system was at rest at time t equals 0, and our position, that's going to be equal to 0. Okay, so if we're writing that out in, I guess, math form, whatever. If our system is at rest at time t equals 0, that's going to be x of 0. So x at times t equals 0 is going to be equal to 0. All right, so let's plug this in now into our general solution here. So we have x of 0 equals 0. And we have C1, E, I'm just going to write e to the 0 because again, we're basically plugging the 0 in for time t plus C2 e to the 0 plus 0.821 cosine of 0 plus 0.662 sine of 0. Let's do some simplification. We have 0 equals C1. So remember, e to the 0, that's just 1. So we have 0 equals C1 plus C2. And then plus 0.821, because cosine of 0 is 1, and then sine of 0 is 0. Okay, so let's rewrite this now to C1 plus C2 equals minus 0.821. And then I'm going to call that equation 1. Okay, now we're going to differentiate this. So we'll do x dot of t. So we have x dot of t, that's going to be equal, oops, should not put 0 there. So basically we're just going to differentiate what we had up top here for x of t. So we're going to have x dot of t equals minus 1.6 c1 e to the minus 1.6 t minus 8.1 c2 e to the minus 8.1 t. So now just remember your chain rule. Minus 0.821 sine of t plus 0.662 cosine of t. Okay, and then we're going to plug in for, again, for our initial condition. So since we had x of 0 equals 0, then we have x dot of 0 is going to be equal to 0 for our velocity. And then I'm going to do the same thing like I did last time. So minus 1.6 c1 e to the 0 minus 8.1 c2 e to the 0 minus 8.21 sine of 0 plus 0.662 cosine of 0. Let's simplify. Again, I write out a lot of my steps just so it's very explicit. 0 equals minus 1.61 minus 8.1 c2. And then sine of 0, that's going to go away. And then we're left with plus 0.662. And then let's rewrite this. We have C1 and C2 on the left-hand side. So I'll do minus 1.6 C1 minus 8.1 C2 So I'm really moving 0.662 to the left-hand side. Kind of think of it like that. Okay, so that's going to be equal to negative 0.662. And I'll call this equation 2. So now we have, again, two equations and two unknowns. We can solve for this simultaneously with a calculator because we don't feel like doing any work. And then we can solve for that. C1 equals minus 1.12 and C2 equals 0.3. Okay, now we can plug all of this into what was our general solution. So that was just right here. Okay, so we're going to plug in right there. So we have x of t equals minus 1.12 e to the minus 1.6t plus 0.3 e to the minus 8.1t plus 0.821 cosine of t plus 0.662 sine of t. What a great equation. All right, there we go. Yeah, it's beautiful. All right, so that kind of sucked, right? It sucked solving it by hand. You're going to have to do that again for the lab. But we're going to compare that analytic solution to what we solved graphically, basically inside of Simulink, and then we'll compare those graphs. And again, they should be the same. So what I'll do right now is I'm going to show this graph inside of Simulink, and I'll show basically this analytic solution compared to what I made inside of Simulink, and you'll see that they're very similar. I'm not going to show how to make the model today. Again, we're going to go over making the model next week, but I'm going to show, I'll probably start off the class showing how to make this model inside of Simulink, and then we'll work on the model as a class, making the model for the project, or sorry, for the experiment. Okay, so if you didn't write this down, then it's on Canvas, so yeah, or you can just watch this video again. I'm going to share my screen right now. My Zoom on my other computer has seemed to basically disappeared. Okay, now I got it. Okay, so I'm going to open up MATLAB now. Okay. So this is what we're going to have next time. This is lab 1 right here. I need to remember where I put the one from last time. Yeah, here we go. All right. So here's my script here. So again, we're going to go over this next time, but here's the script, and I'll open up the model as well. So again, Simulink, it takes a little bit to open up, kind of slow. But this will be the general layout that we have for our next experiment. We're going to define what we know. So we solved through some of this today, like our cable stiffness, the mass. We know the damper as well. Okay, so stuff like that. And then we're going to import our Simulink model here. So this line of code will say just run the simulation. And then we're gonna make some plots. So yeah. Okay. Here is our graph, or sorry, our Simulink model for what we just went over for that ODE. Let me run this right now. Okay, I have an error because I first need to run the script. Let's run the script. All right. So here's our Simulink model. So I'll just briefly go over this right now, but we'll go over it in depth next time. So right here is our cosine forcing function. So that was 5 times cosine of t. Was that it? Let me check. Yeah, that was 5 times cosine of t. So basically, here I had a sine function, then I converted it to a cosine function by just taking the derivative. And then we multiply it by a constant, which in this case was 5. And then here is the other part of our ODE. So this was basically the left-hand side. So we have our acceleration, velocity, and position. And then we're multiplying it by our constants that we had. So this was basically, I can't show both of them at the same time, but all of this right here is basically x double dot plus c divided by mx dot plus k divided by mx. All right. And then let's go back here. I'm going to run this one more time. So here's our solution. So I think I need to increase the step size, or basically make the step size smaller, and it would look even more accurate. So you'll see that in the experiment, or I might have had some kind of rounding errors when I was doing the analytic solution. But for the lab, these two lines that we're going to have, they should be very, very close, even closer than this is right now. So the dashed green line, that's the analytic solution. And then kind of hard to see here, but the dotted blue line, that's the solution from Simulink. So both of them are going to work, but Simulink is going to be a lot less work for us. So I'll kind of show you why it's beneficial to use Simulink and not solve for this stuff by hand, especially when it gets to more complex differential equations. All right, so that's all I got for today. Next time we'll make the model. Any questions on what we did today? All right, well, if there's no questions, then again, that's all for today. And I'll see you guys next week. But if you have a question, I'm going to stick around for a few minutes.
Thanks, Professor.
Mhm.
Thank you.
Yep, have a good weekend. Yep. See you guys. See you next week. Did you have any questions, Kobe?